We have the magnetic circuit in figure 4 below has the following values. I is equal to 4 amps.
Yep.
N is equal to 400 turns.
Slow down, 4 amps.
Yep.
Yep.
The N is equal to 400 turns.
Okay, so this is what this is going to be for.
Yep.
Is your magneto-motive force.
Right.
Okay. So what other info have we got?
Okay, the other info we do have, sir, is we've got amps.
Oh, okay, so we've got a steel bar which goes all the way around
Yep.
here. Yeah, we see the turns there. Beautiful. 4 amps, 100 turns. Okay. So then we've got, let's have a look, current, 4 amps, cross-sectional area. So that's that bit there, is 900 millimeters squared. The length path of the steel or iron is 1,250 mil.
Yep.
The distance between here and here is 1.5 millimeters. Got 1,200. 1,200 is the relative permeability of the steel. So that's saying it's 1,200 times better than air.
Yep.
But air has a absolute permeability, mu0, of 4 pi times 10 to the minus 7. That's your strength, it's saying henries per metre. That's so then we've got the relative permeability of the air is 1. Okay, so I'll just write some of those things down. So we said that the relative permeability of the steel is equal to, so the relative permeability of the air, steel is 1,200 times better than that of air.
Right.
We said that we had, that's the 400 turns, so I should use a different colour there. So then we said that the absolute permeability of the air is 4 pi times 10 to the minus 7. Now, this gap here is a bit too wide. We said that that was in the order of 1.5 mil, so that's going to be more like that. Okay, so that face is 900 millimetres, that's what we said before, so the area is equal to 900 millimetres squared. The total length of the steel or iron is 1,250 millimetres, we said. Okay, and let's do some sums. Okay, so magneto-motive force is equal to AT or IN, number of amps, so that's 4 amps times 400 turns. Right, 400 turns, which equals 1,600 ampere turns. So there's my voltage, my magnetic voltage, magneto-motive force. Okay, so what we have then is a series circuit of steel or iron interrupted by an air gap. So I basically have a piece of steel, if I unfold it, which would have a length of 1.25 metres. I've converted millimetres to metres, and it has 900 millimetres squared there. So 900 millimetres squared. So there's 1,000 times 1,000 millimetres times 1,000 millimetres, which would make 1 million millimetres squared. So there's a million of them. So I go 6 decimal places. 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 decimal point 0.0009 metres squared. Okay, the distance here between there and there is 1.5 millimetres. Yeah? Okay, so that's a linear. To convert the 1.5 millimetres, I'll write that down. So the air gap, so that's the length of the iron, and the length of the air gap is equal to, and let's convert that to metres. So what did we say it was? 1.5. So convert that. I move it 3 decimal places. 1, 2, 3. There's my decimal point. 0.0015 metres. Okay. So just do a pause.
Okay.
Give yourself a breather. So there we go. There's our 400 turns. And we had 4 amps there, so that brings the picture up. Okay, so we have an we've got flux going from south to north now. What we want to do is calculate, we have the relative permeability. We know it's 1,200 times better than air. We now need to figure out what the absolute permeability is of the steel or the iron. So we know that it's 1,200 times better than air, conducts. So the steel conducts magnetic lines of force 1,200 times better than air. So we multiply that by the absolute, which is 12.566, which is what 4 times pi is, times 10 to the minus 7. Okay. So So that's the absolute permeability of air multiplied by a number which is 1,200 times better. Pause. So 1,200 times 12.566 times 10 to the minus 7 equals 0.0015079. So I'll write that down. 0.0015079. There we go. Okay, so that is the complete permeability of the iron core. Okay, so then what we do is the absolute permeability. So then what we say is we need to convert that to reluctance. So the reluctance of the iron is equal to the inverse of that number, mu. So that means if the conductivity of the magnetic field gets better and better and better, because that's on the bottom line, as that number gets better, that number is going to reduce. The resistance to the magnetic lines of force is going to go down as that goes up. The larger the number on the bottom line, the smaller the answer here will be. But we also know that if we want to increase the reluctance, we increase its length. So length goes on top. The longer the piece of metal, or for that matter, the longer the conductor in electrical, the larger the resistance will be. But we now put the area on the bottom line because we know that if we diminish the area, we make the area smaller, we're going to make the resistance bigger. So the resistance to the magnetic field, which we call reluctance, will get bigger if the area is reduced. But if the area is made bigger, then the reluctance will reduce. So we go length, the length of which is 1.25 metres over the mu that we just did, 0.0015072 times the area, which was at A, keep going, 0.0009. And at this point we'll pause so that we can work this out. Equals. Take the thing off the pen without losing the number on the calculator. 921,062.7148 ampere turns per Weber. Okay, that's done. Now we have to calculate the air as well. So what I can do there is now we're looking at the resistance or reluctance of the air in the gap here. So let's write that down. That also is the length of the air gap, over the mu absolute, that needs to be absolute too, multiplied by the area, same area. And we said that the length in this case was, that one there, 0.0015 metres over the absolute permeability of the air, which is 4 times pi, which is 12.566 times the area again, which was 0.0009. That's good. And we'll pause so I can calculate it. Okay, so that yields, if I can get the gain, that yields 1,326,330.309. Now we have the reluctance of the steel, which is 1.25 metres long, the reluctance of the air, which is only 1.5 millimetres. So that 1.5 millimetres of air is offering over a million, just 1.5 metres, as compared to 921,000 for the whole length of the bar. Okay, so if we add both they're in series. Look, the air is in series with the steel, so they're in series. Just add them up. So we just do this. We go 13 carry the 1, 2, 10 carry the 1, 3, 9, 3, 7, 4, 12 carry the 1, 2. So what we have is a total reluctance of both the air and the steel at 2,247,393 point. Oh, by the way, I'll just come back to something. There's ampere turns per Weber. Now, you might have noticed that before I left out that. I put that back in. I'm sorry about that. We don't ever forget that it's explained at -7. Now we know the reluctance. And it makes it simple. So just put that on pause. So now we can see, is that running? We've got what we just calculated on the board, RFE, reluctance for the air, the R total, The next question is asking the total flux. Calculate the total flux. They've given us the formula. So this is just Ohm's law.
It is, yep.
So we've got Fm magnetomotive force as compared to the voltage, which would be electromotive force. This is magnetomotive force, is I times R, isn't it?
No.
And we've got a circle there. So we need to find the Webers, or the flux. So that means we divide by R, that makes the formula I is equal to Fm on reluctance, like this. And we said that reluctance before was 400 turns by 4, which was 1600 ampere turns. And we divided it by that number down the bottom there, which was 2,247,393.023 ampere turns per Weber. Notice that those two actually cancel down. Look, see, it leaves us only with Webers. So I just need to pause that for a sec.
True.
Equals, here we go. So I'll use a different colour. Why don't we go for blue? And the answer is 0.007119. 0.000719. 36. 36. Webers was the only thing left. Webers, yay. So finally, the last part of the question asks us, if we just look down here, to calculate the flux density, and it even gives us the formula. B is equal to Webers on area, or flux on area. So B, the very same B, which gives us the formula, B is equal to BLV, or F is equal to BLI. Got to be careful there, it's not a B, that one. So what does it say? How do we generate electricity? We generate electricity when we pass a conductor of length.
Velocity.
Right, conductor, we pass it, velocity, through a magnetic field. So a conductor moving through a magnetic field produces voltage. So there we go. So B is equal to flux over the area. And the flux is what we just saw there, so I don't even have to write it again, over the area of 0.0009 metres squared, which we got up here, right? And I just need to calculate that, so we can pause it while I calculate it. Hang on. Keep rolling, Owen.
Yep.
Okay, so that gives us 0.79104 Teslas. Okay, now, the way I look at this is whenever we play with Teslas or we talk about B's a magnetic field, we talk about that being a magnetic field too. What I generally think of this is a stable field that doesn't change. And generally we punch that as a static number into the calculator, whereas with this, we generally associate phi as delta phi, the change in flux over the change in time. And the change in time. Now the change in time and the change in flux is where we get that velocity thing here, the speed at which we have the relative motion across the conductor is reflected in that as well. The collapsing magnetic field, the change in the magnetic field in a given time. Okay, so then we say that the voltage, or the E, is equal to the number of turns. Number of turns is linked to the length and the velocity of the collapsing magnetic field. So when we talk about flux, we generally talk like this, and when we talk about flux density, it's more a static number. So that's how I differentiate. So that would be like the coulombs, equivalent, analogous to the coulombs, while this is analogous to the current. Right? Current is coulombs per second. Right? So you could say that the Webers, or the flux, is the moving, while the B is the more stable, dense. That's how I look at it anyway. It might not be very scientific, but that's one way of differentiating them. All right. One at that.